Okay, good afternoon, ladies and gentlemen. We will soon hear the invited lecture by Aner Shalev on group theory. Let me introduce the speaker shortly. Aner Shalev is a professor at Hebrew University, Jerusalem, Israel. He received his doctorate in 1989 at Hebrew University under the guidance of Amitzur and Aviman, with a dissertation on group rings. During his distinguished career, he proved several spectacular results in group theory. Just to mention a few, Aner proved a co-class conjecture on finite P groups in 1994. With Martin Liebeck in 1996, he proved that almost all finite simple groups are generated by a pair of elements, one of which has orders 2, the other has order 3. Moreover, a randomly chosen pair of this type is almost certainly generates the groups, though with high probability. He was also a co-author of a paper which appeared in 2010 that completed the proof of Orer's conjecture, stating that every element of a finite simple group is a commutator. Generalizing this result, in 2018, he proved with Guranik, Liebeck, O'Brien, and Tieck that other word maps are also surjective, so have the similar property on finite simple groups. But he's not only publishing mathematical works. He published some novels. His greatest success was the book titled Dark Matter, which had been translated into German, Italian, and Czech. Aner was an invited speaker at the ICM, the International Congress of Mathematicians, in 1998. Now he's an invited speaker at the ECM, which is a more selective conference because we have much less invited speakers here. So I know that Aner is a superb lecturer, and despite of the technical difficulties which might occur here, I'm looking forward to a very nice talk. So Aner, it is, now I try to share the screen and you will talk and I try to follow your talk with the presentation. So Aner, please.
Thank you, Peter P-Cube, for your warm introduction. And thank you. I want to begin by thanking the organizers for inviting me. I have never been to Slovenia, and I feel almost there, and I will surely come at some point later. What I'm going to talk about is subset products and derangements. Derangements are permutations without fixed points. So the talk in the end of the talk will be related to this topic, and the subset product will be something which is related but is more general and has more applications. I'm a little bit, at least now, technically or always technically challenged. So so Peter shares the screen, and can we move to the? Okay. Before. Okay, no. Let's stay here. If you see, there was a subtitle: 2 is greater than 3. I will not explain what I mean, but maybe you will understand during the talk. Okay, so first, the definition of subset product. It's kind of, if you have a group G and 2 subsets of G's, and then subsets A, B, then the product A, capital B is what you see on the screen, or products of all elements from A with every elements of A and with elements of B. And similarly, similar definition for longer subsets A, B, C. And indeed, we will be mainly interested in only those two cases, subsets of length, products of length 2 and products of length 3. Okay, let's move on. Great. So in our case, G will always be finite, and usually it will be a non-abelian finite simple group. And needless to say, we invoke the classification of finite simple groups. So there are some natural questions. One is what can we say about the size of the product in terms of the size of A and B, or A and B and C, and another related question is, when is the product everything? When is it equal to G? Okay, so there is a very deep and celebrated theorem which is related to the first question to estimate the product size. And this is the so-called product theorem, which is part of a fascinating deep theory of approximate subgroups. Independently and essentially at the same time, it was proved by Brouillard, Green and Tau, and Piber and Szabo. The years which you see here are the first number, 2010, is archive publication, and journal publication is the second, also. Okay, so anyway, what is the theorem? It says that if we have a finite simple group of Lie type of bounded rank, for example, you can think about P, S, L, N, Q, where N is bounded, then there is epsilon depending only on the rank R, such that if we take any subset of G which generates G, then either A cube is G. Okay, every element of G is a product of 3 elements from A, or A cube, its size is much larger than A in the sense that it's the size of, at least the size of A to the 1 plus epsilon. Okay, this, of course, probably many of you know these famous results. It extends pioneering work by Helfgott about PSL to P. And there is another very nice approach by Udi Rushovsky, who applied model theory to approach this problem. Great. So now let's give you another related background, so-called quasi-random groups. So it's something, there is a famous paper of Tim Gowers about this, and there are other contributors which I'll mention. So now let G be any finite group. And so we can look at irreducible and complex characters, chi of G, and among all the non-trivial one, the trivial is just the one, we take the minimal degree of a non-trivial character, and we say that a family of groups is quasi-random if, as we let the groups, if mg tends to infinity, as the size of G goes to infinity, provided G is selected, of course, from this family F. For example, it is easy to see that if F is all non-abelian finite simple groups, then this set of groups is quasi-random. A lot is known about their characters, their character degree, so this is trivial using current knowledge. Now, what is it good for? There are various applications of these ideas, but a very nice one is the so-called Gowers trick, which is implicit in Gowers, which is actually in Gowers' paper in 2008, and Nikolov and Piber also proved it and derived many applications. There is also a nice paper by Nikolov and Piber, which is related. So it says that if we have three subsets A, B, C of G, and now G is any finite group, and the product of their sizes is at least the size of the G cube divided by this invariant M of G is bounded below, then ABC is G. Okay, this has various consequences. For example, if we take A equals B equals C, then obviously what we get is that if the size of A is at least mg to the minus third times the size of G, then that's enough to conclude that A cube is G, not P cube. Okay, now if F is, in general, if F is a quasi-random family of groups, finite groups, and epsilon is any fixed positive number, could be very small, and G is in F, and ABC are subsets of G, such that their sizes or their proportion is bounded below by epsilon. Let's say it like this. Then we also have, in this case, ABC is G, if G is sufficiently large. So this is this follows immediately from what we say, and another comment is that this applies for finite simple groups. Why? Because we just said that the family of finite simple groups is quasi-random. Okay. Now, can we extend results on products of length 3 to products of length 2? So you see now the number 3 and 2 are starting to star here. Let's move on. So usually the answer is no. There are examples showing that if we take products of two subsets, then essentially you don't have growth and you don't have covering. So this is a bit upsetting, but maybe we shouldn't give up. So let's try to find some conditions when the answer is yes, namely we can replace 3 by 2, therefore derive better results in a way. Okay, so a trivial observation, so this is a rare positive answer, is where the subsets A, B of G are so big, they're bigger than half of the size of G, and in this case, A, B is G. The proof is trivial. It's not even an exercise, I think, but anyway, it's one line which is written here, and this is best possible if we have if you try to replace 2 by 3 here in the denominator, you won't get it. Okay, but this is trivial, but it will be useful in some crucial step in the end of the talk. But usually we said that we cannot replace 3 by 2. So let's make another assumption that we deal with normal subsets, Rs, say, of G instead of arbitrary subsets. So normal subsets are, of course, subsets which are close to conjugation. They are union of conjugacy classes. And they appear very often in group theory. So this too is interesting. In a paper with Martin Liebeck and my ex-PhD student Gili Schul, we showed that essentially, if we take small normal subsets, maybe I will not read the whole theorem, you see it clearly, but if we take small normal subsets and we estimate the size of the product, then the size of the product will be really almost as almost as large as possible, okay? Because of course, the sizes of the product is always bounded by the product of the sizes, but in this case, it will be bounded below by the size of R. The size of Rs is the size of, at least the size of R times the size of S to the power 1 minus epsilon, which epsilon depends on the size of the sets. So, so if we take R equals S, we also get huge expansion. As you see, R square, its size will be almost the size of R square, the size of R to the 2 minus epsilon. Okay, so in a way, there are some advantages. This is not as deep as a product theorem, but it uses some various tools, but it's not so sophisticated. Anyway, it has some advantages that, unlike the product theorem, this holds for all finite simple groups. The product theorem only holds, if I may remind you, for groups of Lie type of bounded rank. Okay, so this holds for all finite simple groups, and we in the product theorem we get 3-step growth, and now we get 2-step growth. So it is, in this sense, it is much stronger, but of course under the assumption that the subsets are normal. Okay, but the disadvantage is that we accept normality. We assume that this that we have small subgroups and small subsets, and unlike in the product theorem. Okay, just to illustrate why even products of normal subgroups of normal subset are sometimes very difficult to investigate, is a famous still open conjecture of John Thompson. So as written here, some of this kind of problems can be notoriously difficult. And Thompson's conjecture is that every finite simple group has a conjugacy class C whose square is the whole of G. Okay, so so it is very easy and elementary, just 1 or 2 lines to deduce Ore's conjecture from Thompson's conjectures. And after we prove the Ore's conjecture, we and others really wanted to go another step forward and to try to prove Thompson's conjecture. This conjecture is known in various cases, but it's still open for some, infinitely many, some families and of finite simple groups of Lie type over tiny fields with at most 8 elements. There is important work by Ehlers and Gordev dealing with larger fields. Okay. So you see, when you can't prove the whole thing, you try to prove approximate things. So let me just mention some approximations to Thompson's conjecture. So in 2008, I tried a probabilistic approach to the conjecture. So the idea is that if we take a finite simple group and we take an element X at random, and we take its conjugacy class C, then it would be very nice to say that with probability going to 1, C square will be G, but this would be a proof of Thompson's conjecture, and we don't have a proof, but it says that the square of a random class in this sense is almost all of G. Even there is a result about random walks, that the mixing time of the corresponding random walk is 2, and from this you can say that the size of C square is at least 1 minus epsilon times the size of G, almost surely for every tiny epsilon. as G goes to infinity. So see, it's a little bit absurd. On the one hand, we don't know to prove Thompson's conjecture, but on the other hand, we say that almost all classes almost satisfy the conjecture. Okay, there is another work with Larsen and Michael Larsen and Pham Thiep, that if we have a finite simple group of a notoriously large order, I don't even want to pronounce this number, it's much bigger than the number of particles in the universe. So every this huge finite simple group has two conjugacy classes, not one, whose product is everything except possibly the identity element. So, and the proof is quite complicated. And then there is another similar result by Guralnik and Male, getting rid of our ridiculous huge number and proving it for all finite simple group. They also needed to use some computational group theory, but that's fine. So you see, so we do have kind of Thompson's conjecture, but for two different classes. Okay, to illustrate also why motivations for studying normal subgroup, I want to discuss a little bit word maps, which Peter also mentioned in his introduction. So a word is an element of a free group, let's say freely generated by x1 to xd, and every word, usually I will, all my words are assumed to be non-trivial. There is not much interest in the trivial word one. So if given a group G, we may always substitute elements of G, Gi instead of Xi, a generator of the free group, and thus get a map, a map from G to the D to G. Associated with this word, and this is what we mean by word map. We denote by WG the image of this map. Now, WG is obviously a normal subset. You see it immediately that, you know, if you conjugate, you can conjugate the element inside, and actually there is a very important and influential result of Borel from 1983 on word maps, which really started the theory of word maps, saying that word maps on simple algebraic groups are dominant in the sense of algebraic geometry, and this started a very long project, three, maybe more than 3 decades in a way, to study word maps with focus on finite simple groups. So, for example, there are various results also by Saxel Wilson and by Martinez Zelmanov about power map. If the word is, let's say, x to the k, this is a power map, and this word was already studied nicely in the 90s. General words were studied a little bit later. So, for example, Michael Larsen proved that they have word maps have large image in some sense that I will not describe now, but he used Borel's theorem. Actually, he reproved Borel's theorem and then had this conclusion for finite simple groups. Okay, so you see that the image of a word map on a finite simple group is always a large normal subset. Of course, it can be one if the group satisfies this identity, but what I mean large is, my approach is asymptotic. So when the simple group gets larger and larger, then the image will get larger. Okay, now there are several results about, let's call it word width, namely how many how if we take a power of the image wg to the something, when will we get g? We will surely get g at some point. It's easy to see, but what is the minimal power which does it? And so in 2001, Martin Liebeck and I proved that wg to some c of w is g, but this of course we have to assume that we don't have an identity. So let's say that the group is sufficiently large, but for sufficiently large group, the exponent CW doesn't depend on the group, only on the word. Somehow there is a Nikolov-Segal, there is a series of Arnold's papers, so also Nikolov-Segal have published 2 papers, and they used the word width to solve a problem, a very nice deep problem of Serre on profinite groups. Probably you know it, but philosophical way to ask it is whether the algebraic group of a profinite group determines the topology. This is not the way Serre formulated, but it's okay. Let me tell you what Serre's problem is. If you take a finite index subgroup of a finitely generated, topologically finitely generated profinite group, Serre asked whether every finite index subgroup should be an open subgroup. Okay, and Nikolov-Segal provided a positive answer in 2 papers in the Annals. Let's go further down. Okay, now if we take 3 words, non-trivial words, of course, W1, W2, W3, and we look at the images of those 3 words, it turns out that the product of the normal subsets W1, G, W2, G, W3, G is G, provided G is sufficiently large in terms of these 3 words. So that's a result of mine, and then there were some improvements in joint papers with Larsen and Tiepp. So again, we move down from 3 to 2, and so in 2011 we showed that two subsets are enough. So W1G, W2G is already G, provided G is sufficiently large. And in 2018, we were more interested in probabilistic aspects, and there was a certain conjecture which we managed to prove that if we take 2 disjoint words, which means words in disjoint sets of variables, and we take the product, then it induced almost uniform distribution on finite simple groups with respect to L1 norm. Okay, so now you can ask yourself, so these are results about certain large normal subsets of finite simple groups related to words, but maybe results like this hold for in general for large normal subsets of finite simple groups. Okay, so let's take ST to be normal subset of a finite simple group G, and suppose that their proportion is bounded away from 0, their size is at least epsilon G. So one question is, does the product ST contain all non-trivial elements of G if G is sufficiently large? We have to, okay, let's go on. Sorry. Now the second question is even more optimistic or ambitious. Now we don't, the first is about covering, the second is about distribution. So the question is whether the number of solutions to the equation G equal little s times little t from big S and big T respectively, the number of solutions is roughly the size of S times the size of T divided by the order of G. And this means an almost uniform distribution in the L infinity norm, okay? Now, one can also ask what is the situation if S equals T? Maybe that's a better situation and we can prove stronger result. And another question is, what is it good for? Of course, it will generalize some things which we have seen already, but maybe there are other applications. So let's say that to exclude the identity in questions 1 and 2 is necessary. Let's not go into the technical details, but it's quite easy. Also to assume that the subset S and T are normal in questions 1 of 2 is also necessary. If we don't assume normality, we can get a counter example, but let's move on. And this is absolutely a trivial observation that the positive answer to question 1 and let's go back, Peter, that if we, that question 2 implies namely almost uniform distribution, implies covering, namely implies, so positive answer to question 2 implies positive answer to question 1, and let's go on. Okay, now we hoped in the beginning to provide the positive answers to question 1, the covering question, for all finite simple groups. The drawback is that it's hard to prove wrong results. So this is why we didn't prove it. But what we proved it is something weaker, but true, hopefully. So let's see the situation. So the answers to questions 1 and 2 are negative if G ranges over all finite simple groups, or even just over alternating groups, or even just over all projective special linear groups. So this is kind of a big failure, you know. Now, part 2 of the theorem is that if S is T, it does help in some cases. The answer to question 2 is still negative for alternating group if S is T, but in part 3 you see that in this case the answer to question 1 is positive for alternating groups. Okay, so at least we have the first positive result for S equals T and for alternating groups. And the last part of the theorem is the more optimistic part, is that if G is a group of Lie type of bounded rank, then the answer to questions 1 and 2 are both positive. And also, of course, 3, which was a particular case. Okay, so let's give some details. Okay, let's move on. You see a theorem here, but it's a little bit technical, and we don't have too much time. So let's stay here. But essentially, what we see is that even if S and T are almost half the size of the group, their product will not cover. Okay, now, but if S is T, then we were able to show something even stronger than we formulated in the question. So in this case, we obtain a covering result, a positive answer to question 1, even when epsilon is not bounded away from 0, but going to 0 quite fast. So you see here the theorem. So epsilon can be allowed to be, for example, e to the minus n to the 1/5 or something like this for alternating groups. In this case, we get that the t square is an. Okay, there is a sketch of proof here, but let's see the whole page first, and let me just say that it's basically character methods. Some exponential character bounds for symmetric group in a paper with Michael Larsen. And we also needed some nice results for Erdős-Turan series of papers, classical paper on statistical group theory. But it's basically character methods, the proof. Now, what about classical groups? So again, they are bad in the general case. Let's continue. We can prove something of for products of length 3 for classical groups, which is stronger than what Gower's trick will give you. Okay, and here we need also character theory, and basically it's a level theory of character of character bounds, which was developed by Bob Guralnik, Michael Larsen, and Pham Thiep. They have 2 papers, and they are very deep and long papers, and so also even these results, even though it's about products of length 3, it's deep, at least in the sense of the tools the proof uses. Okay. Okay, let's move on. Okay. Now we said that groups of Lie type of bounded rank are good, and let's move to a theorem, and the theorem says that a more detailed theorem that if we take such a group, and if we have two normal subsets of size bounded away from proportion bounded away from 0, then the probabilistic question 2, has an affirmative answer. Here in the theorem, we should assume, of course, that G is not the identity element. So this is a but question 2 has a positive answer, and this implies that all questions 1, 2, 3 have affirmative answer for this type of groups. Okay. Now the tools combine algebraic geometry and character theory. So, for example, a classical result of Frobenius, which is written here, and all kinds of exponential character bounds, and also let's move on. We also need the Langevin estimates from algebraic geometry and some other stuff. And okay, and so this is what we I have to say about questions 1 and 4. But now let's see the applications, which are maybe will be more interesting to some of the audience. Okay, so let's see applications to word maps. In a paper which I already mentioned with Larsen and Thiep, we prove something that if we take the product of many disjoint words, and the length depends on the length of the product depends on the length of the words, then we get almost uniform distribution as a group size tends to infinity. But if we take another probabilistic model, we don't need such huge products. Products of length 2 are enough. So it follows from what we said before, that if we now we choose a random elements from W1G and another random elements from W2G, and we multiply them, and we want to see the distribution and how uniform it is. So it is essentially a uniform distribution with just length 2. So this is this is a corollary of the fact that Lie-type groups of bounded rank are good, as we defined. And there is previously already Nikolov and Piper proved something similar for length 3 products. Okay. Now, the main application, which is for derangements, for fixed point free permutations. This topic has a long history.
Fortunately, I don't think we have time for the long history. So just...
Yeah, yeah. So, okay, but it started, 3 centuries ago, and let me just remind you that transitive groups, finite transitive permutation groups, always have a derangement, a fixed point free permutations. And Nigel Boston and I conjecture that they have many derangements in the sense that the proportion is bounded away from 0. Okay, so let's move on. Now, Fullman and Goralnik worked for almost 20 years about this conjecture, and with several, maybe 4 very nice papers with other application, and eventually in 2018 they proved our conjecture, and this implies that all sufficiently large transitive simple permutation groups, for all these groups, every permutation is a product of 3 derangements, and this follows from previous results on general normal subsets. Now, again, we are obsessed with making 3 to 2. So can we replace 3 by 2? So for bounded rank, it is trivial corollary from what we said before. For bounded rank, every element of a large enough finite simple transitive permutation group is a product of 2 derangements. But only those groups were good, and the other groups were bad in some senses. So how should we proceed? So we want to deal with classical groups of unbounded rank, of course. Now there are several. Let's see the whole slide. There are several related works and conjectures, but let's jump to the corollary that if that classical groups of large rank also have derangement widths too, with some exceptions, which you see in the corollary. Okay. Now let's say that, okay, there are now some last stages of the proof, but Peter, I think we really don't have time. Maybe just in one sentence, we kind of we prove it for various cases, but then there is another case that that requires another method, and then there is a third case which requires another method, and you almost lose patience, but eventually the proof was completed. So let's move on. So the upshot is this theorem, let G be a finite simple transitive permutation group. If G is sufficiently large, then every element of G is a product of two derangements, of two fixed point free permutations. What's not so nice here is that the sufficiently large, you know, in our conjecture, he doesn't say sufficiently large, for example. So why should we say it? So a natural question, and this is a question also for the audience, I would really love to see. We are tired of derangement, so I would love to see other experts working on this. Okay, so are there any exceptions? Our conjecture is that no, that there are no exceptions. And this is actually supported by nice computations which Eamon O'Brien has done. He provided really very strong positive computational evidence, so also small finite simple groups, but very big, and you need big computers to check them. Also, we didn't find, Eamon didn't find any counter example. And I think what remains is to thank you all for your attention and to wish you all good health.